Greetings. Okay, this session is going to be about the titration of a commercial antacid. This is the lab. But before we talk about that, I'm going to give you some background material. Okay, so first let's talk about what is an acid and what is a base. Now we're going to keep it simple here. Okay, for now we're just going to say an acid is something that donates protons, and therefore a base is going to be something that accepts protons. Okay. Now, the question is, where do you find protons? And the answer is a proton is just a hydrogen nucleus. Remember, if you take away an electron, there's the proton. So an H plus ion is just a proton. So if we look at something that everybody seems to know, this is the acid found in the stomach, hydrochloric acid. Just HCl, pay attention, HCl is really, it's a gas actually, and it's hydrogen chloride gas. So what makes it an acid? Well, when you put it in solution, and there's an AQ, it's supposed to be a Q there if you can see it, sub Q, A sub Q, okay, that's aqueous, all right. Then in solution, it gives up that proton. So there's the proton that you see given up. Okay, I'm just fixing the pen. Okay, so it's a proton donor. Okay, proton donor because there's the H plus. Okay, and we would say that this is actually a monoprotic acid because it gives up one. Okay, so here's a neutralization reaction. Okay, you should know this reaction. Neutralization reactions when you add an acid and a base, and what comes out always, the remaining products, okay, are a salt. Now, salt, there's more than one salt, okay? There's many different salts and water, okay? H2O. So here's a simple thing. If we take HCl aqueous, hydrochloric acid, and add it to a base, NaOH, okay? Then, of course, we can say this is a replacement, a double replacement. We get the salt out, and there's the water that we get out, okay? So all neutralization reactions, you get a salt, some type of salt, and you get water out. Okay. If instead of HCl, if we use KCl, right, that's potassium chloride. I can't even say the acid, but it's an acid, and this would be KCl. Okay, and KCl, potassium chloride, is a uh, salt. Okay, is that what I want? No, that's not what I want. I want the, it doesn't matter. Okay, forget that. I was trying to do something. All right, so let's move on. So again, the HCl, hydrochloric acid aqueous, breaks up into H plus in solution and Cl minus. Okay, and again, it's monoprotic because it's giving up one proton. Okay, one proton. All right, so let's look at something called sulfuric acid. Okay, sulfuric acid is H2SO4, again, aqueous, because in solution, these two hydrogens break off, H plus, and there's our old friend, the sulfate ion, SO2 minus. Okay, so sulfuric acid, we say, is diprotic because it's giving away two protons. You see, one, two. Remember, hydrogen nucleus is a proton. Another example would be phosphoric acid. Okay, phosphoric acid, H3PO4. Once again, aqueous because in solution, these three hydrogens dissociate, H plus, H plus, H plus, and there's our friend PO4 minus 3, the phosphate ion. Okay, and we would call this a triprotic because there's three protons being given off, being donated. Okay, so when we talk about acids and bases, we need to say, well, how do you know if it's an acid or a base? So how do we measure acidity or alkalinity? Alkalinity is a measure of how base the system is. Okay, to do this, we need what's called a logarithmic scale. Okay, so we got to talk about logarithms. Okay, so let's go on. Okay, so let's do this. So let's first talk about ordinary water, tap water. Okay, let's distilled water, perfect water, clean water, not our water. Okay, in ordinary water, there's a very, very slight, and it's naturally occurring dissociation. Dissociation means breaking apart. Okay, so this is dissociation. Oops, get the pen going. Okay, this dissociation of water. Okay, so here's a water molecule, H2O. Notice the arrow goes both ways. There's an arrow going that way, and there's an arrow going that way, right? It's reversible. Okay, so H2O breaks up into a hydroxide ion, OH minus 1 was one of our polyatomics, and there's our proton. Okay, now this really, a lot of people say this proton's hanging out, but really this proton then, this H plus, mixes with another water molecule down here. Okay, so if you take H2O and you mix it with an H plus, we get our hydronium ion, H3O plus. Okay, and it's really this concentration that tells us whether we have an acid, because right, this guy wants to go the other way and it wants to donate a proton, you see? So when we talk about the pH scale, essentially this is the percentage or amount of hydrogen. Okay, so, and hydrogen ions are going to come from this hydronium. Okay, so in room temperature, essentially in ordinary water, only about 1 in 10 million molecules, that's 1 over 10 to the 7th, water molecules dissociate. Okay, so that's 10 to the minus 7. Okay, so the concentration would be 10 to the minus 7 water molecules produce hydronium. So the concentration of hydronium ions would be 10 to the minus 7. Okay, that's also the concentration of these H pluses. So this would be 10 to the minus 7. But that's also then, because there's a coefficient here of 1, there's a coefficient here of 1, there's a coefficient here of 1, right? They're all this is balanced, right? So there'd also be 10 to the minus 7 of these. There would be 10 to the minus 1 out of 10 to the minus 7 water molecules. Okay, 10 to the minus 7. So we could put that coefficient in front of everything. So if there's 10 to the minus 7 hydronium ions, there's 10 to the minus 7 hydroxide ions. That's the concentration. Now, the notation is in a square bracket. Square bracket denotes concentration. So in ordinary water, we have the concentration of hydronium is 10 to the minus 7. And I just said the concentration of hydroxide ions is also 10 to the minus 7. When you take the product of 10 to the minus 7 and 10 to the minus 7, the product of the hydronium concentration, 10 to the minus 7, and you multiply it by the concentration of hydroxide ions, 10 to the minus 7, we get 10 to the minus 14. Okay, so now we're ready for logarithms. And here's where you say, I can't do logarithms. I can barely do fractions. All right, let's look at how easy logarithms are that we'll be doing. Okay, so don't be afraid. Even you can do it. Okay, all right, so let's watch. Okay, well, let's look. The log of 10 to the first power to 1 is 1. The log of 100, 10 to the second, is 2. The log of 10 to the third is 3. The log of 10 to the sixth is 6. Boy, to the third is 3. The log of 10 to the sixth is 6. Boy, this is hard. Well, what about the log of 10 to the minus 5? Well, it's negative 5. The log of 10 to the minus 11 is negative 11. The log of 10 to the negative 13 is negative 13. The log of 10 to the minus 8 is 10 to the minus 8. Gee. That's all you need to know about logarithms. So even you can do the logarithm, okay? So now we want to talk about the pH scale, okay? So let's see. So we're going to define the pH scale, as we'll see. It's going to be involving the concentration, okay? So let's look. All right. All right, so, I don't think it came out on the last slide. Let's look again. No, it's not really coming out. All right, so let's go here. Let's go back. So let's go to the next page, and I'm going to define pH. Okay, so let's define pH. All right, which has to do with the hydronium concentration. Okay, so here's the definition of pH that didn't come out on the last slide. Okay, pH is defined to be negative the log of the hydronium concentration, H3O plus. Okay, it's going to be negative the log. Okay, so let's do some examples. Here's some simple examples. Okay, if the remember, square bracket is concentration. Square bracket is concentration. Okay, remember the square bracket is concentration. Okay, so if the concentration of hydronium ions in whatever solution you're looking at is 10 to the negative 6, then the definition of pH is minus the log of the hydronium concentration. So it's negative minus the log of 10 to the minus 6. So it's minus, remember the log of 10 to the minus 6 is minus 6. So a negative and a negative gives a plus. pH is always plus. Okay, if the pH is less than 7, it's an acid. If it's equal to 7, it's neutral. And if it's greater than 7, it's a base. Okay, so pH equals 7 is neutral. I'm sure most of you know this already. And a pH that's greater than 7 would be a base or alkaline. Okay, so let's do another example. If the hydronium concentration is 10 to the negative 13, okay, 10 to the negative 13, then the pH is 10 to the negative, then the pH is minus the log of 10 to the minus 13. So it's negative, the log of 10 to the negative 13 is negative 13. Negative, positive number, it's 13. See how easy this is? If the hydronium concentration is 10 to the minus 2, then a pH is minus the log of 10 to the minus 2. So it's negative minus negative 2 is plus 2. Wow, this is really hard, isn't it? All right, let's go on. Now, suppose instead of giving you the hydronium concentration, I give you the hydroxide concentration. Why would he do that? Oh, so mean. All right, well, let's see. If the OH concentration, not hydronium, OH, the hydroxide, is 10 to the minus 5, well, what is the pH? Well, let's look. Remember, the product of hydronium concentration times the hydroxide concentration must always be 10 to the minus 14. Always be 10 to the minus 14. Okay, so if the hydronium concentration is 10 to the minus 5th, that means, the hydroxide concentration is 10 to the minus 5. That means the hydronium concentration must be 10 to the minus 9, because negative 9 times 10 to the minus 5 is 10 to the minus 14. So the pH is minus the log. Hydronium concentration is 10 to the minus 9. So it's minus 9 is plus 9. Okay. If the hydroxide concentration is 10 to the minus 10, well, if it's 10 to the minus 10, oopsie, there we go. If it's 10 to the minus 10, then the hydronium concentration must be 10 to the minus 4, because 10 to the minus 4 times 10 to the minus 10 is 10 to the minus 14. So the pH then is minus the log of the hydronium concentration. So it's minus the log of 10 to the minus 4. So we get negative. A negative 4 is plus 4. Okay. Play it again. If the hydronium concentration is 10 to the minus 8, right, 10 to the negative 8, then the hydronium concentration is 10 to the minus 6. right? Since 10 to the minus 6 times 10 to the minus 8 is 10 to the negative 14. So the pH is, again, the negative the log of the hydronium concentration. So it's minus the log of 10 to the minus 6. So it's negative, a negative 6 is plus 6. Okay, and finally, one more example. Okay, if the hydronium concentration is 10 to the minus 3, then the hydroxide concentration, I might keep saying hydronium. If the hydroxide concentration is 10 to the negative 3, then the hydronium concentration must be 10 to the minus 11, because 10 to the minus 11, 10 to the, 10 to the minus 11 times 10 to the negative 3 is 10 to the negative 14. Okay, so if the hydronium concentration is 10 to the minus 11, then a pH is negative 10 to the log of 10 to the minus 11. So a negative 11 is plus 11. And there we have it. We're experts now on calculating pH. That's as hard as it gets. If I give you the hydronium concentration and or if I give you the hydroxide concentration, you can figure out the pH. Okay, let's go on. Now, back to the lab. So now we have an understanding of acids, which are proton donors, bases, which are proton acceptors, the pH scale, okay? And now we can talk about the lab, which is titration of a commercial acid. Well, here's a new word for us, titration. What does titration mean? A titration is where you use the concentration of a known, you have the known concentration of a substance, and you use it to find the concentration of an unknown solution. Okay, so we're going to do titration of a commercial acid, and we're going to do neutralization. Okay, so the commercial antacid is going to be Tums. Okay, and the excuse me, and the base is calcium carbonate, because in solution, calcium carbonate, if I do CaCO3, right? If I do this aqueous 3, right? If I do this aqueous, okay, remember, this is chalk and limestone. In water, this breaks up into Ca ions, and you get CO3. The carbonate, remember, this is carbonate. I'll write that here, carbonate, polyatomic carbonate. Notice it has a -2 charge, so it wants to add 2 protons, you see? So it's a proton acceptor. So calcium carbonate is a base. Now remember, our neutralization reaction, always an acid plus a base always gives a salt, some type of salt, and water. Okay. Now in the lab, we're going to be using hydrochloric acid, the same acid that's found in the stomach. Okay. So if you put hydrochloric acid, right, in water, right, it's going to break up. Right? Well, it's acid, it's breaking up this. So hydrochloric acid wants to donate a proton. So take that proton, okay, take that proton that's donated from the hydrochloric acid, there's the proton, and add it to calcium carbonate, okay? And the hydrogen then wants to go there, right? And if we do it twice, because this still needs this needs 2 protons, then we get this, H2CO3, okay, which actually breaks up into a gas, carbon dioxide gas and water. But again, it goes both ways, okay? So the purpose of the lab is to determine how much acid is neutralized by the Tums, by this calcium carbonate. Okay, we got to try to figure that out. Okay, and how in the world can we figure that out? Well, let's see what we can do. Let me try to illustrate what's going on in the lab. Okay. So in the lab, we're going to take a tablet of Tums, and it's going to be wintergreen. Keep in mind it's wintergreen, so it's going to have a greenish hue, a greenish color, okay, and flavor if you eat it. Okay, and what we're going to do is we're going to take that Tums. There's my Tums, my little dark thing. Okay, whatever. Okay, it's not a great picture. So there's my Tums, right? And we're going to crush it up in a mortar and pestle. Okay, we're going to crush that. And some of you use this in cooking. We're going to crush this up into a powder. And then we're going to mix this in with 50 milliliters of hydrochloric acid. And we know the concentration, okay? We'll know the concentration. We'll talk about concentration later, not in this lecture, okay? Maybe I'll talk about it. Good. So we're gonna mix the Tums with 50 milliliters of hydrochloric acid. Now, the question is, how much of these 50 milliliters of hydrochloric acid did the Tums neutralize? We don't know. Okay, we don't know. So that's what we want to try to figure out. So here's what we're gonna do. We're gonna boil, right, in lab. We're gonna boil this mixture of Tums and hydrochloric acid for a couple minutes, 3 to 5 minutes. Then we're gonna add an indicator, phenolphthalein. Remember, this mixture, unless the Tums neutralized everything, this mixture of 50 milliliters of hydrochloric acid plus the Tums should be acidic, right? So phenolphthalein won't do anything. Remember, phenolphthalein turns pink in a base. All right. So remember, this thing is going to have a greenish color because the Tums was a little wintergreen flavor. Now we're ready to titrate this. And what we're going to do is we're going to add a base, sodium hydroxide now, to our mixture. Okay, sodium hydroxide. Sodium hydroxide is NaOH, and it's what's used in drain cleaners. Okay, it's a nice strong base. Okay, so remember, we have mixed our Tums into 50 milliliters of HCl, but we don't know how much of this hydrochloric acid is neutralized. We just don't know, and that's what we want to try to determine. Okay, all right. So here's what we're going to do. We're going to slowly, drop by drop, add some sodium hydroxide. This is our titration procedure, to our Tums and HCl mixture, okay, through a burette, right? There's the burette, and we're going to drip, drip, drip NaOH, okay? I'm going to drip, drip, drip. This is the NaOH. Oops, get the pen. All right. So that's NaOH, sodium hydroxide. We're dripping it. It's a base. Remember, this is still acidic, but we don't know how much of it is acidic, right? Because the Tums, right? The Tums neutralize some of this 50 mLs of acid, but we don't know how much. We don't know how much Tums neutralize. That's what we're trying to find out. Now, when this system becomes neutralized and just starts becoming a base, right? So as we add the sodium hydroxide, it becomes more and more basic, right? It becomes less acidic, more basic. And when it just wants to become a base, remember, phenolphthalein turns pink in a base. But because of the wintergreen color, instead of turning pink, the phenolphthalein will make the mixture turn purple because the wintergreen color of the liquid, because of the Tums, plus the pink color from the phenolphthalein when it turns base will make the solution turn purple. Okay, so we need to carefully observe when this mixture just begins to turn purple. If it was a clear mixture, then upon just turning into a base, the phenolphthalein would, of course, turn pink. However, since our mixture has wintergreen color due to the Tums, upon just turning into a base, the color of the mixture will be wintergreen plus pink, which looks a little purplish. Okay, so for example, here's just an example. It's not what you get in lab. All right, if 30 milliliters of NaOH are needed for our solution to turn purple, that means of the 50 mLs of the hydrochloric acid plus Tums mixture, means 20 mLs was neutralized by the Tums, because you still need 30 mLs of a base to make it turn into to neutralize the entire 50 mLs. If 23 milliliters of NaOH are needed for our solution to turn purple, then that means that 27 milliliters of the 50 mLs of HCl were neutralized. Okay, I can't read the bottom, so we'll go on. Okay, so I think that's pretty much it. That's what we're doing in the lab. We're going to try to neutralize, see how much of the NOH was neutralized by the NaOH. Okay, and however much NaOH you need, that means the Tums did not neutralize that. Okay. Let me just say a couple words about concentration of solution. Okay. Here. So remember, so I want to talk about concentration of solutions for a bit. Concentration of solutions. Concentration of solutions. So what do I mean by concentrate? Well, it's the concentration of solute in the solvent. Okay, so if I add 5 spoons of sugar into a cup of, coffee, that's the concentration. It's 5 spoons per cup. If I add 8 spoons, that's the concentration. 1.5, 1.5 spoons, that's the concentration. So it's the concentration of solute over to solvent. Okay. Now chemists have many, many, many ways of measuring concentration. Okay. What we're going to focus on is the measure of concentration. Measure of concentration. This is all we're going to do. Measure of concentration is going to be called the molarity. Molarity. Okay. And yes, it depends on moles. Okay. So the molarity is going to tell us the concentration of a solution, the concentration of solute to solvent. Okay, so let's define molarity. First, let's recall what a mole is. Remember, if we have a mole, 1 mole of anything, of chairs, of molecules, of anything, remember, was approximately equal to, it's 6 point something, but we don't care, 6 times 10 to the 23rd of that something. Okay, and we said that this number was called Avogadro's number. Avogadro's number. Okay, and we wrote that as N sub A. So for example, if I have N sub A C atoms, so if I have 6 times 10 to the 23rd carbon atoms, we look on the periodic table and we see the mass number of carbon is 12. So this would be equal to 12 grams. If I did O atoms, if we look in a periodic table, you don't memorize this stuff, the mass of oxygen, if you have Avogadro's number of O atoms, then it would be 16 grams. Okay. If I had Avogadro's number of H2O molecules, well, hydrogen has a mass of 1, so you'd have 2 times 1 gram for the 2 hydrogens, and then you'd have to add in the mass of oxygen, which was 16 grams, right? And so that's equal to 18 grams would be 1 mole of water would have this mass. 9 grams of water is a half a mole, 0.5 of a mole, or 0.5 Na, water molecules. Okay, so we know what a mole is. Okay, so what we want to define now is molarity. Okay, so I'm going to define molarity. Remember, molarity is a measure of concentration. Molarity. Molarity is a measure of concentration. A measure of concentration. Okay, so let's define it. Molarity is equal to number of moles of solution of of solute divided by 1 liter of solvent. So this will tell us the concentration in molarities of solvent. So for example, something pretty easy, okay? Let's take NaOH. NaOH. 1 mole of this stuff, well, I need the mass of sodium. Well, if I look on the periodic table, that's 23. Take the mass of oxygen, plus 16, look it up, plus the mass of hydrogen, which is 1. So 40 grams of NaOH is 1 mole. So we would say a 1 molar solution, 1M, this is a 1 molar solution of molar solution of sodium hydroxide sorry, it's a little crooked. Okay, we would write this as 1M of sodium hydroxide, 1 molar solution is equal to, so 1 mole is 40, 1M of sodium hydroxide, 1 molar solution is equal to, so 1 mole is 40 grams of NaOH divided by 1 liter. Ta-da! What about a 0.5 M solution? Well, a 0.5 M solution would be 20 grams over 1 liter. A 6 M solution would be 6 times 40 is 240 grams over 1 liter. A 0.3 M solution would be 0.3 times 40 is what? 12? 12 grams divided by 1 liter. Okay, so that's what molarity is, and that's how we do this. Suppose I had, let's do one more. Suppose I wanted to know how many grams of H2SO4, right? And I have H2SO4, and I want a 0.4 M solution, molar solution of this stuff. Well, first we have to get the mass of 1 mole of this hydrogen sulfate. Again, aqueous, if I put aqueous, it's sulfuric acid. All right, so 1 mole would be 2 times the mass of hydrogen, which is 1 gram, plus the mass of sulfur. Again, look on the periodic table. I believe it's 32 grams. Plus, now I need 4 oxygens, right? Because there's 4 oxygens, so it's 4 times 16. Okay, so this is equal to 2, that's 34, plus 4 times 16 is what? 64 grams. So that would be what? 98 grams. Okay, so a 1 molar solution of hydrochloric acid would have 98 grams in 1 liter. A 0.4 M solution, you need 0.4 times 98 grams. 0.4, make it a little neater, divided by 1 liter. Okay, so 0.4 times that is what? 36, 39.2, if I do that in my head. 4 times 8 is 32, so it's 3.2 plus 36, yeah, 39.2 grams in 1 liter. Okay, so this would be a 0.4 M solution. If I wanted a 2M solution of hydrochloric acid, we multiply it by 2, so we get 180, 196 grams. divided by 1 liter. Okay, so this tells us the concentration. So in lab, you'll see when we have the NaOH, right? It made the bottle, well, the bottle may be listed as a 0.36 m NaOH solution, OH. Okay, that means it's a 0.36 molarity. Remember, this had a mass of 40, so you'd have to multiply by 0.36 to tell you how many grams per liter there are of sodium hydroxide with the concentration of 0.36. Okay, so concentrations measured in molarity, and molarity is the number of moles of solute divided by 1 liter of solvent. Okay, I hope this helps. All right, take care.